So to wrap up today, we are going to look at the two major kinds of waves. So these first animations, I want you to take a second and pause the video to take a look at how these two main types of waves compare and contrast. Think about what's the same between the two and what's different between the two. So the top animation there was what we call a transverse wave. So think for a second about how you would move to make this wave. If we were in the classroom and had a row of students sitting along the lab tables, how would we create a motion that looks like this? The trick in observing both of these kinds of waves is to pick any one dot and follow its motion. It's easiest to see this with the dots that are fairly close to the edges of the wave. And take a look at what that one individual dot is doing. And compare that to the motion of the wave as a whole. So then take a step backwards and follow along the pulse of energy. So I see a crest that is moving along the wave this way, while any one of these little dots is just moving up and down. So a transverse wave also often gets referred to as traveling because we have that sense of motion. We're going to look at some special cases next week where that won't necessarily be true. And the key definition of this transverse wave is that we have the particle motion up and down with that wave energy traveling along towards the right-hand side of my screen. And these are at right angles to each other. And this actually is the definition of a transverse wave, that the particle motion and the energy propagation are at right angles to each other. The second animation is what we call a longitudinal or compression wave. And this is how sound waves work. This would also be how a vibration through a metal bar or something like that would work. I find this one a little harder to see than the first one, but it still has that sense of moving along towards the right-hand side of my screen. And again, if I pick any one dot, and it is easiest with dots closest to the edges because the straight line gives a reference point, that one dot is just moving from side to side. So I can draw the same kind of picture for a longitudinal wave as I did for a transverse wave. I have the particle motion as being an oscillation back and forth, and then I have that wave that's propagating energy towards the right-hand side of my screen. And the main definition of a longitudinal wave, just like how the transverse wave, these were at right angles to each other, a longitudinal wave is defined as the particle motion and the wave motion being parallel. So in the case of sound, this is the vibration of air molecules, and you can hear me speaking because my vocal cords vibrate at particular frequencies, which makes the air molecules right next to them vibrate, which hit the next molecules and make them vibrate, and so on and so on and so on. And if we were in the same room, that vibration would translate all the way to your eardrum, and your eardrum would vibrate because of that vibrating air, and your brain would interpret that vibration as the sound of my voice. We're in a little bit of a different situation today because we're using a digital pickup here, but the premise is the same idea. So if I freeze my longitudinal wave here as a screenshot, I can still talk about the same properties of a longitudinal wave as I did with a transverse wave. We're just not used to seeing it in quite the same way. But if I pick any one point, and I go to the next point where the pattern starts to repeat itself, That is a wavelength. I could also do it from there to there. I can't illustrate the amplitude in the same way. Instead of crest and trough, the words we use here are compression, where we have a high density of particles, and something called a rarefaction, which is just the technical term for the area of low density. So the features that these two kinds of waves, the transverse and the longitudinal, have in common is what leaves us with our basic definition of what we mean by a wave. So what they have in common is this oscillation or oscillatory motion or repetitive. This repetitive motion on the part of the individual particles, creating overall a disturbance that transfers energy. From one place to another. And most of these have the added condition of that traveling from one place to another happening through a medium or a material, except for EM radiation.
So given all these properties of the different kinds of waves and how we perceive light and how we perceive sound, where we're going in this unit is looking at how these basic properties affect each other, how different waves can interfere each other, specifically looking at different sound and light phenomenon. Where we're going to spend most of our time looking at sound, but we're hoping we'll have a little bit of time towards the end to look at some of the interesting electromagnetic radiation phenomenon that we can see. This is normally the point, or the beginning of this lesson would have been the point where I would ask you, what do you already know about waves, or what's your experience with musical instruments, or since we've been talking about pitch already, do you have perfect pitch, and then do a little test of that. Unfortunately, we're in a little bit of a different scenario where we're not here to talk about those kinds of things or talk about what your experience is or what you've already learned. So I hope today has been mostly things that you've heard before. And then where we'll go in the next few weeks is mainly in chapters 11 and 12 of your textbook, looking at how we observe these different properties on a day-to-day basis. So stay tuned.